discussed about cascaded amplifiers. Now, the problem with cascading is gain can be reduced. It may reduce the gain. Although you can increase the bandwidth, gain will be reduced. Now, if you do not want to reduce the gain, but you want to eliminate the Miller effect, then cascading may not be a good option. Then we can look at alternative option. Alternative option is a source coupled amplifier. So instead of a drain coupled amplifier, drain to source, source to source. Here we are connecting source with source. So two amplifiers, source with source. So source coupled amplifier. This is also called unilateralization. When source is connected to source, this is also called unilateralization. In this, if you look at the figure, the CGD, both the CGD are in series, which means total effect is half. If you connect two capacitors in series, total effect will be half. So CGD is not Miller multiplied here, and the impact of CGS is now half. And so that is half. That becomes half. So CGD is no more Miller multiplied. So this is how, using unilateralization, using source with source coupling, we can remove the impact or eliminate the impact of Miller effect to a large extent without affecting the gain. But bad news is, in this case, in this arrangement, if we go for such a circuit, signal must go through the source node. CSB becomes significant because signal has to go through the source. Source is connected to source. So signal has to go to the source node. And so CSB will be significant. Power consumption, therefore, since that will be significant, power consumption will be doubled. Analytical that you can see, Zin is equal to, in this case, for this circuit, do the analysis. Zin is equal to 1 by S, CGS by 2, because CGS become half. So that becomes CGS by 2 plus CGD. There is no Miller effect, so CGD into 1 minus AB is not there. So it is S into CGS by 2 plus CGD. So that if you use the 0.18 micron CMOS, then this is approximately equal to 1 upon S into CGS into 0.95. 0.95 means power consumption is double. Instead of CGS by 2, it is CGS. CGS into 0.95 is approximately CGS. So instead of CGS by 2, it is CGS. So 2 times the power consumption. So power consumption becomes double. Yeah. Next. Now how to do this neutralization? Look at this circuit. In this circuit, what we have done is, gate and drain we have joined using a capacitor and an amplifier with gain -1. Gain -1 means what is the meaning of gain -1? Means the phase is inverted. That was gain is 1, and gain remains 1, phase is inverted. So we are using an op-amp there, operational amplifier or amplifier, any amplifier you are using, so that we are putting a capacitor, additional capacitor we are putting. If you put a capacitor, so this Cn is equal to CGD. If Cn is equal to CGD, then the charging of CGD will be provided by Cn now. Consider cancelling the effect of CGD. How to cancel that? Use another capacitor. Charging of that capacitor will be provided by CGD. because CGD will discharge to RL and charge it CGN. What is the benefit? Benefit is impact of CGD will be reduced because Cin, now if you look at the input capacitance, so Cin will be CGS will be there, plus with Miller effect CGD will be 1 plus 1 minus AV into CGD. Then the other one, the Cn, that part is minus 1, so AV is minus 1, so that will be minus 1. Absolute you will take, that will plus 1, so 1 plus AV into CG. If you add them together, it is CGS plus 2 CGD. Same as in cascaded amplifier, but without cascading. There is no cascading, but the effect is same as the cascaded amplifier. So using neutralization is a better choice among all the choices. I assume that neutralization is the best choice. Now what are the issues here in the neutralization? Issues are what happens if Cn is not precisely exactly or precisely equal to CGD. So in this case, Cin is approximately equal to CGS plus 1 plus AV into CGD plus 1 minus AV into Cn. Now since it is not exactly CGD, so they will not cancel out. So some amount, residual amount will be. So since the neutralization does not completely remove the effect of CGD, you can make Cn slightly larger than CGD. That will over neutralize. Slight more Cn, slightly larger Cn will over neutralize. Cn equal to CGD will neutralize. Cn slightly larger than CGD will over neutralize. Now over neutralize will reduce the effect of CGS because you are connecting them in series. So that will reduce the effect of CGS. But if CGN is too large, the input capacitance is negative because of minus AB. If Cn is very large compared to CGD, it will be negative and it will be very difficult to stabilize. Why? What will happen if it is too large? If it becomes negative at high frequency, negative capacitance means it is an inductance. So it will lead to inductive input impedance. Instead of capacitive, it will become inductive. Now, the question is how we are going to invert the amplifier. How can we create inverting amplifiers? So, for practical implementation of neutralization, what we will do is we will leverage the differential signaling to create the inverted signal. Look at this circuit. In this circuit, Cn, suppose for the fast amplifier M1, Cn is not connected to RL of M1. Cn is connected to RL of M2. Similarly, for the second amplifier M2, the Cn is connected to RL of M1. That is what we are doing. We are using the differential signaling to create an inverted signal. Only issue left is matching Cn to CGD. How do you match Cn to CGD? Either we use a CMOS transistor for Cn and appropriately bias it to get Cn is equal to CGD, or slightly over bias it, over neutralize it, or mostly people use metal capacitors, metallic capacitor instead of polycapacitors. People use metallic capacitor. That is very good. If Cn is too low, there will be residual influence of CGD. If Cn is too high, input impedance becomes inductive. So these are the two drawbacks or the two issues. Okay, next. Then there is another method which many people do not like. This is called shunt-peaked amplifier. In the shunt-peak amplifier, an inductor is used. People do not like this because of inductor. You know, inductor basically is very bulky. its size is large. It is like a spring, so size is large. So inductor is used to extend the bandwidth. Instead of capacitance, we are going to use inductance. So inductance will be used. Now to avoid the size effect, you can use a spiral inductor. So mostly in the chips or circuits, instead of a spring type of thing, we use a spiral inductor. So often it is implemented in the form of a spiral inductor. Now we can view the impact of the inductor in both time and frequency. In the frequency, the effect of inductor is peaking the frequency response. So the peak to frequency response will peak at a particular frequency. Before that it will be slower. After that it will be lower. It will peak at a particular frequency. So peaking of frequency response is one issue. Then in time, because it is an inductor, it will be delayed. So it will delay the changing of current in RL. So current change in RL will be delayed. So the main purpose of high speed may get affected. Issue is using the inductor, shunt amplifier, if you use it. Is it possible to extend the bandwidth without significant peaking by keeping it constant? By keeping the gain constant, gain should not peak with frequency. Is that possible? Let us see. So first let us do the analysis. Here is the circuit. Left side is the circuit. Right side is its equivalent circuit. You can do the analysis of the equivalent circuit easily. Find out what is AV. AV is equal to GM into Z out. Now Z out is equal to series combination of RL with LD, that is in parallel with C total. That is what is Z out. So AV is equal to GM into SLD plus RL, that is series combination, that is in parallel with 1 by SC total. So if you do the series and parallel calculation, then it will be GM into RL into in the numerator you will get S LD by RL plus 1. Denominator you will get S square LD C total plus SRL C total plus 1. Now let us use parameterization. So we will use some parameters. First parameter is in the numerator. You can see there is a term LD by RL. So I will use a parameter tau which represents LD by RL. So for LD by RL we will use tau. So that is for the first parameter. In the denominator we have LD. In the first term we have got LD, we have got C total. So what I will do is, in the denominator, in the first term, let me divide it by RL and multiply by RL, the first term. So the first term becomes S square into LD by RL into C total into RL. Now LD by RL is tau, so it will be S square into tau into C total into RL. Now C total into RL, let me define this as M into tau. RL into C total, let me define it as M into tau. So the first term becomes S square into tau into M into tau, which means first term is S square into tau square into M. Second term will be S into RL into C total. RL into C total is M into tau. Also S into M into tau, the second term. Third term is plus 1. So by parameterizing, AV is equal to GM into RL. In the numerator we will get S into tau plus 1. In the denominator we will get S square tau square M plus S tau plus 1. Now here we can see there are two terms, RLC total and LD by RL. Now RLC total is a time constant, is equivalent to a time constant, so that is time constant RC. Similarly LD by RL is equivalent to a time constant. That is why we are using tau. M is unitless, tau can be in seconds. So RC to tau, those time constant we are taking. M is the ratio of RC to LR time constants. Now after parameterization, we got AB is equal to GM into RL whole into, in the numerator 1 plus tau S, in the denominator S square tau square M plus S tau M plus 1. Now we will do a comparison of new and old 3 dB frequencies for this. 3 dB frequencies means the frequencies where the gain becomes half. So in the new, after parameterization where the frequency becomes half, before parameterization where frequency becomes half. So that before parameterization we have already seen where the frequency becomes half. After parameterization, let us compare them. Now in this what we will do, we will set S is equal to J omega. Omega 1 we have already seen before parameterization. Omega 1 is equal to 1 by RC. After parameterization we have seen tau is equal to 1 upon omega 1 m. So AV, magnitude of AV is equal to GM RL into magnitude of J omega by omega 1 into n plus 1 in the numerator. In the denominator we will get minus omega and by omega 1 m square into m plus j omega by omega 1 m into n plus 1. So simplify this, do a simple algebraic calculation. This part will now become for dB, the 3 dB frequency, this gain has to be half, which means power has to be half, which means gain has to be 1 by root 2. So AB has to be 1 by root 2, assuming GM into RL is equal to 1. Under that condition, this should be the term under the absolute sign or magnitude part, that should be 1 by root 2. So this implies that j omega 2 divided by omega 1m plus 1 in the numerator divided by minus omega 2 omega upon omega 1 m square into m plus j omega 2 upon omega 1 plus 1 should be equal to 1 by root 2. We have to solve for omega 2 by omega 1 because omega 2 is the new frequency, omega 1 is the old frequency, which is 1 by RC. Omega 1 is 1 by RC. Omega 2 by omega 1 we have to find out. Let us find out omega 1. Now the first equation that we have seen in the previous one. Do some algebraic manipulation and solve this for omega 2 by omega 1. So omega 2 by omega 1 will be this factor. Square root of 3 terms. The first term is minus m square by 2 plus m plus 1. The second term, which is added to the first term, is square root of 2 more terms, minus m square by 2 plus m plus 1 whole square plus m square. Now from this we see that m will directly set the amount of bandwidth extension. M is equal to 0 means this is equal to 1. Yes, this is equal to root. M is equal to 0. This will give you root. And other values of m will control it. So once you choose m, then we can find out what is the inductor value. Because we know m is equal to m, we have already seen m is equal to RL into C total divided by tau, tau being LD by RL. Therefore, LD is equal to RL square C total by M. So once we choose M, then we can find out inductor value, what will be the LD. RL is known, C total is known, so we can find out what is LD. Now we look at the plot of the bandwidth extension versus M. M is in the x-axis, y-axis is omega 1 by omega 2. Now we can see that the highest extension of omega 1 by omega 2, that is where the peaking occurs, is for M is equal to 1.41. So if you choose M is equal to 1.41, there the peaking in frequency occurs. Omega by omega 2, that peak value it is slightly more than 1.8. It is around 1.85. So that occurs at now M is equal to 1.41. Omega 1 by omega 2 is equal to around 1.85 when M is equal to 1.41. Peaking occurs for M is equal to 1.41. Now look at the transfer function. Transfer function means gain versus frequency, both in dB. So both we are taking both gain versus frequency in dB. Gain in dB, frequency in dB. Maximum bandwidth, if you look at this curve, you get maximum bandwidth when M is equal to 1.41. Extension is 1.85. Omega 1 by omega 2 is equal to 1.85. Sorry, yes. Omega 1 by omega 2 is equal to 1.85. That is the extension, that much of extension. Maximum extension is that you get 1.85. So that you can see the red curve is for M is equal to 1.45. That gives you the maximum bandwidth. Maximally flat. Now in the maximum bandwidth you can see gain does not remain constant. Gain starts to increase after about when the normalized frequency is 1 by 10. So after 1 by 10 gain goes on increasing to the peak value, then after the peak it starts dropping. So it is not constant over the whole bandwidth. Bandwidth is up to 1. Suppose for the red curve the bandwidth is up to 1 by 100 to 1. Over the whole bandwidth it is not constant. It is not flat. The second case is maximally flat response. This is called maximally flat response because over this bandwidth the gain remains constant. M is equal to 2.41. Look at the curve, blue curve, where gain is equal to 2.41. There up to 1, our normalized frequency is equal to 1 up to that point. The gain remains constant. Then we look at the phase response. The best phase response that we get for M is equal to 3.1. If M is equal to 3.1, extension is 1.6. Omega 2 by omega 1 is equal to 1.6, but that gives you the best response, best phase response. There is no phase distortion. In the other two cases, there can be phase distortion. Then suppose you don't have the inductor, M is equal to infinity. There is no inductor. If M is equal to infinity, no inductor, that case is the black curve. And no inductor means there is only one pole. So that is about around 1.10, then it ends, there is no extension. I diagrams you have not understood yet, so I will not go to the I diagram. In the communication you will read about I diagram, then maybe you can use it. Now let us consider the zero peaked common source amplifier. because we do not want picking. So the best thing is to go for zero pick. So zero picked common source amplifier. Let us consider it. This circuit diagram shows you a zero picked common source amplifier. Here in the source we are using the R and C. So with the source we are connecting R and C in parallel. R, C are in parallel, they are connected in series with source. So RS and CS, these are connected to source. So these two are connected here. Now the question is why? Why we will go for RS and CS? Answer is simple. That I told you in the beginning. Inductor is bulky, inductor is expensive. These are two things. And so if you are going for a spiral inductor, it is expensive. So since these are expensive with respect to die area, people try to avoid inductors. We use R and C instead of inductors. So can we instead achieve bandwidth extension with capacitor? That is what we are trying to do. Zero peak common source amplifier. In this, we are trying to extend the bandwidth with capacitor instead of inductor. Idea, what is the idea? Idea is degenerate the gain at lower frequency, remove degeneration at higher frequencies. So at higher frequency, create a zero. Issue is we must increase RL to keep the same gain at the lower poles, and we have to lower the achievable gate voltage bias. Now look at this zero peaked common source amplifier analysis. What we will do is we will add CGD to C total, as we have done previously. Similar analysis. Previously means last class. So same analysis, same circuit we are using. We have a voltage source VI, then CGS, then voltage dependent current source GNVS, then V0 is output, ZL is the load, ZS is the for RL RSCS we are using ZS or the impedance at the source. Okay. Now what is ZL? ZL is equal to RL in parallel with 1 upon SC total. And what is ZS? ZS is RS in parallel with 1 upon SCS. Now what we will do is we will ignore the feed forward effect of CGD, and on that we will ignore, so CGD is not here. You will see that there is no CGD here, and that effect is ignored. Then the analysis, using the analysis you can find out what is V0 by VI. Do a circuit analysis, simple circuit analysis will give you V0 by VI is equal to GM into ZL divided by 1 plus GM ZS plus SGS ZS. Sorry, SCGS ZS. Now let us continue with this. Assume that omega is less than omega t and Gm is much greater than SCGS. Then the transfer function now can be simplified as GMRL into 1 plus S RCCS in the numerator, and in the denominator 1 plus S RLC total into 1 plus S RSCS plus GMRS. Now, if you look at this, what we are doing, so we can do is we can add a 0 at 1 by RSCS, which means we will make 1 by RSCS is equal to 0. That is how we are going to add a 0 at 1 by RSCS. When frequency f is equal to 1 by RSCS, there we will get 0. But we will introduce, once we do that, we will introduce a second pole at 1 plus GMRS by RSCS. How we are going to do that is very simple. In the numerator, take common RSCS, you take common in the numerator. So the numerator becomes, in the numerator take S RSCS common. So numerator becomes GMRL into 1 plus 1 by SCS RS. In the denominator also take SCS RS common. So the denominator becomes, the first part will remain as it is. Second part will be 1 plus 1 by S RSCS plus and GMRS by S RSCS. In that term, you can neglect RS, or you can cancel out RS from the numerator denominator. So that will become GM by SRS. Okay. So you can get this. So second pole will be, from that you can see that the second pole is at 1 plus GMRS by RSCS. Now at the lower frequency, we have to reduce the lower frequency. So the gain will be reduced at the lower frequency to GMRL by 1 plus GMRS. That will be the gain at the lower frequency. First pole is at 1 by RLC total. That can be cancelled by making RSCS is equal to RLC total. So if you make RSCS is equal to RLC total, the first pole is equal to second pole. So the first pole is cancelled. Then the bandwidth is extended up to the second pole. There is no first pole, only second pole. Bandwidth extends up to the second pole. So now let us do the analysis for 4 0 cancellation. RSCS is equal to RLC total. That is the point that we have made. So doing this, we will cancel the first pole. Now V0 by Vi will be GM into RL by 1 plus S RSCS plus GMRS. AV at DC, that will be GM RL by 1 plus GMRS. Now, omega H is equal to 1 plus GMRS by RSCS, that will be equal to 1 plus GMRS by RLC total. That is it. Now if you look at this expression, can we say that this is actually increasing the bandwidth? Is it helping the bandwidth? If we design the simple common source amplifier for the same gain, then what would be the bandwidth? If we know what would be the bandwidth, then we know whether this is increasing the bandwidth or not. So for that, first we have to reduce the RL. Load resistance we have to reduce to RDSL. How much? What will be RDSL? That will be RL by 1 plus GMRS. So from where we get this 1 plus GMRS? RL by 1 plus GMRS? Look at ADV. So AV is equal to GM into RL by 1 plus GMRS. So that RL by 1 plus GMRS, that will make RDSL. That we get. AVDC is equal to GM into RL dash. Now the bandwidth is omega h is equal to 1 by RL dash C total, which is equal to 1 plus GM RS by RL C total. So same zero peaked amplifier. So now we have got a zero peaked amplifier using this principle. Now what is the input impedance ignoring the Miller effect? Zin will be, if you remember the circuit, now Zin is equal to 1 by SCGS plus 1 plus GM by SCGS into ZS. There is no AV because we are not considering Miller effect. So AV 1 minus AV term is not there. So Zin is this. Now again we will use this factor. Omega is much smaller than omega t. GM is much greater than SCGS. Now near the upper 3 dB bandwidth, there are 2 3 dB bandwidth points. Near the upper point, that is at omega 2, near the upper 3 dB bandwidth point, SRSCS is much greater than 1. If SRSCS is much greater than 1, then Zin can be approximated as 1 by SCGS, take that as common, into 1 plus GM by SCS. So that we can do. Or Zin S is equal to 1 by J omega CGS minus GM by omega square CG into CS. This can give rise to a negative resistance. The second part, minus GM by omega square CG into CGS and CG into CS. This is a negative term in the Zin. So since there is a negative term, if you get large, say, GM or small omega or smaller CG into CGS, CS, we can get negative resistance. You know, negative resistance results in oscillation. So this can, instead of amplifier, we will get parasitic oscillation. And that is the problem with it, that is the issue. So the actual input impedance Zin total, that has to be in parallel connection between Zin and KCG. KCG is taking the Miller effect of CG. So considering the Miller constant, that we have to do. Now I'll come back to the this inductors again. Shunt and series peak. So picking up the gain under shunt connection and series connection. Combine shunt picking with a series inductor. Here you can see that we are using a shunt inductor and a series inductor, L1 and L2 in the amplifier. If you combine them, that will extend the bandwidth because it converts the circuit to a filter, second order filter. Because it becomes a second order filter, the bandwidth will be extended. So this can be designed by choosing the proper picking, how much picking we require. Increases the delay of the amplifier. This you can look in the book, a term list book. Going to see the details of this circuit and its analysis. And with that, we have come to the end of broadband amplifier. I will take a rest. Next class, we will Wednesday. Anyhow, I will take the class on a Wednesday. Even if it is a holiday, I will take it. We have lost much classes. Many classes we have lost. So Wednesday, we will consider ABCD parameters. So after this, we will stop here. The device part, amplifier part, we will take a break now. We will come back to ABCD parameter. Then the transmission line part, whatever is left, that we will consider from the next class on. So we take a break here. My only advice is you keep on reading, read the book, read the notes, and if you have doubts, mail me or WhatsApp me, send me over WhatsApp, or mail me or ask